called nonparametric tests. They're still hypothesis tests. They still require a random sample, but the difference is that the underlying sampling distribution is not a parametric distribution. That means it's not like a t distribution where you have a continuous scale. It's not a z distribution, the normal distribution. It's not chi-square. It's not f. It's not any of those parametric distributions. So the best we can do is use the critical value approach to make the decision in a setting like this. So our new test, our new hypothesis test, is going to test a claim that was made about a population median, not a population mean. And this table here gives you the critical values. And the test itself is called the sign test. The sign test. And that means really some pluses and minuses, right? So these are positive signs and negative signs. And we're going to attach a positive sign and a negative sign or a negative sign to each individual data value, and that's how it gets its name. But we'll come back to this. Okay, so here is the one sample sign test. It's a nonparametric test, and you'll see it for the first time in chapter 15. There are 3 different tests. Test a hypothesis about the median of a population. And so this M that you see down here throughout is the population median. So compare this test to the test from section 10.3, where we said mu equals mu0 as the null hypothesis. The only difference is that we're going to say in this test that the median is equal to some number. And that number will change depending upon the test. And then we have a 2-tailed test with the not equal to sign, a 1-tailed left test with the less than sign, and a right-tailed test or a 1-tailed right test with the greater than sign. But other than that, the M and the M0 will be the same. M0 is the assumed value of the median, which is what will be given to you in the claim. There are 2 different versions of this. One is if we have a sample size that's less than 25. We're going to use this process here. And then there's another one that if we have a sample size larger than 25, then the sampling distribution, the central limit theorem, guarantees that if we get into around the 30 or bigger range, that the sampling distribution is approximately normal, regardless of what the original underlying population looks like. And so we're going to move to a normal. This is a Z, so we're going to be using a Z distribution, and we're going to be using Z critical values. And go back to how we used that in the past. So the hypotheses are a little bit different. And we're going to be using the critical value approach. We do have a p-value approach as well. But the way that we calculate the test statistic is not going to be with a calculator function or with a fancy formula in this case, but rather it's going to use the signs of the data values. So we'll look at calculating that test statistic here in just a second. Step 2 in the hypothesis test is always the same. Identify the level of significance, alpha. And then here's the by hand approach. We're going to count the number of observations below our hypothesized median, assign them a minus sign, and then count the number of observations above the hypothesized medians and assign them a positive sign. And we'll ignore the data values that are equal to our hypothesized median. The test statistic is either going to be just K, I'll show you how to calculate that in a second, or it's going to be if N is larger than 25, then we're going to use this. N less than or equal to 25, we're going to use this. N greater than 25, we'll use this. And this tells you how to calculate K. K is either going to be the number of plus signs or the number of minus signs in this sign test. We'll get the critical value from the table. And if our test statistic K is less than or equal to the critical value, we're going to reject the null hypothesis. So there's the decision. And then we want to state the conclusion, as we have in the past. All right, let's take a look at an example. And here's number 8, the age of the bride. When you count up the data values, you have 4 by 5, there are 20. So n is equal to 20. And so this is the small case situation. And the test statistic is going to equal K. Okay, so let's take a look at these. Age of the bride. Sociologist feels that the median age, notice we're talking about medians right to begin with, at which women marry in Cook County, Illinois, is less than the median age of 26.9 years old throughout the United States. You may not know this, but the average age of a bride is 26.9 years. That's the median age. So it's based on a random sample of 20 certificates from the county clerk. And this is what we have. Okay. The sociologist feels that the median age is less than. All right, so we've got the null hypothesis and the alternative. We're going to be using capital M to represent the median. We'll define that. The median is equal to 26.9, which is the average. So they're saying the average in Cook County, Illinois is the same thing as the average throughout the United States. And the average throughout the United States is 26.9. So this is a statement that there's no difference between the national average and the median in Cook County. And the alternative is that the sociologist feels that the age is less than 26.9 years. And this is the claim. All right, we have one variable, so we need to define it. M equals the median age of brides in Cook County, Illinois. Here's the level of significance, alpha, 0.05, step 2, and now the test statistic. Okay, here is our M0 value right here. And we're going to compare every one of these data values to 26.9. If a data value is larger than 26.9, we're going to assign it a plus sign. If a data value is larger or smaller than 26.9, like 25, we're going to assign a negative. And that's why this is called the sign test. All right, so go through all the data values, put a plus sign whenever you get a number that's larger than 26.9, and then put a negative sign next to all of those data values that are less than 26.9. We don't have any data values that we're going to ignore here because we don't have any data values that hit 26.9 right on the nose. All right, so our table over here, we have plus signs and minus signs and zeros. So we don't have any zeros, but so 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 plus signs, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 minus signs. Now, it's always the case that the number of plus signs and the number of minus signs, if you add them together, you should get, well, sometimes you won't get n. Sometimes you'll get something less than n if you have any data values that match this mu0 values. But when we're determining the critical value, the value of n we're going to use is the value of the plus signs plus the minus signs. All right, now the test statistic. The test statistic is based on this table. K is equal. It is usually the smaller of the two. It's usually the smaller of the number of plus signs or minus signs, just the way that it works out. All right, now we have a left-tailed test, and so the value of K will be plus signs or minus signs depending upon what the alternative hypothesis says. And here's the test. We have a less than test, so this one here. The test statistic K will be the number of plus signs. So what we're going to do is to go over here and identify the number of plus signs. We have 8, so K is equal to 8. Notice 8 is the smaller of the two, 8 or 12. And then the next thing is we're going to go find the critical value. So I'm going to find this table, and we have a value of alpha. We have a left-tailed test, which is a one-tailed test. Alpha is 0.05. So you have 0.05 in one tail. And then over here, you have the value of n. So go all the way down to n equals 20. And then go over to the far right column. And the critical value is 5. So these numbers in here are critical values. So this is the one we want right here. N is 20, and alpha is 0.05 in one tail. So the critical value is equal to 5. And now the decision. Here's the decision for the small sample case. This is step 4. This is where we make the decision. If the K value is less than or equal to the critical value, then we reject. If this is not the case, then we do not reject. So I guess we could go on to say, if K is greater than the critical value, then do not reject. Go down here, we have K, which is 8, and the critical value, which is 5. And we know that 8 is greater than 5. So K is greater than the critical value. And if K is greater than the critical value, then we do not reject. So the decision here is do not reject the null hypothesis. And then we will state our conclusion based on that. Step 1, hypotheses. Step 2, level of significance. Step 3, gather the evidence, report the test statistic, make the decision, and then interpret the decision, write the conclusion. Okay, so we are not going to reject the null hypothesis. So we don't have evidence to support the claim that married women in Cook County have a lower median age at marriage than the national average. So we would say there is not enough evidence to support the claim that the median age of brides in Cook County, Illinois, is less than the national average of 26.9 years. Okay, so there's no classical approach because we don't have a sampling distribution that is a continuous distribution like the z distribution. So we can't do that, but we do have a p-value approach, and we can interpret the p-value in the same way. If p is less than alpha, then reject the null hypothesis, and if not, we do not reject the null hypothesis. If p is greater than alpha, do not. Same test. All right, here's the p-value, and it turns out that it goes back to something that we've calculated in the past. It is, when you come to a data value like this, like 31, there's one of two things that can happen. It's either above the median or it's below the median. So there's just two options for any one data value. If it matches the median, hypothesized median from the null hypothesis, we're just going to ignore it. So we're going to end up with just pluses and minuses. A data value is above the median or it's below. So two options for every data value. And we can ask the question that, what is the probability that, in a situation where we have two outcomes, that is a binomial setting, what's the probability of getting a certain number of plus signs or a certain number of minus signs in the binomial distribution? So we're going to do it this way. It's the probability that the number of plus signs or minus signs, depending on what it would be, is less than or equal to R value of k in the binomial. So this is binomial, and we want to go CDF here, is less than, and it always has to have n first. Well, our n is 20. I'll write it in here. Then the probability of a data value, well, if this is true, if the median really is 26.9, then we're going to have the same number of data values above with plus signs as with minus signs. Because if the median is this, then what we should see, if there's 20 values here, we should see 10 values above 26.9 and 10 values below. So the probability of getting a plus sign would be exactly 1/2. So it turns out for this test, the p-value that we put into binomial CDF is always going to be 1/2. And then the last number is our k value. So we have 20, 1/2, and then our k value was 8. So I'm just going to go ahead and calculate that here. Bring back binomial. CDF, 20, 0.5, and 8. And that's 0.25, I'll call it 2. But what you need to see is that since p is 0.252 and alpha is 0.05, we have p greater than alpha. And when that happens, we do not reject the null hypothesis. Yeah, unfortunately, with this one, you cannot find the critical value with the calculator. So the critical value is only going to be found by consulting this table here. I don't know if you've ever been to this Zillow.com site. You can actually go there and type in the address of your home or your parents' home or some other relative's home, and it'll tell you the value of their home. And They even have this feature on there called Zestimate, which tells homeowners and home buyers what they think your house would go for, the house would sell for. If it's accurate, then the median difference between the actual selling price and the Zestimate should be 0. So in this one, the median is equal to 0. This is going to be your null hypothesis. That median is a difference. And then here are 10 different homes that were researched on Zillow. And these were actual sale prices, so that after the fact, they could actually compare what the house sold for and what Zillow was estimating it for before the sale. And they could just do the difference to find out how accurate they were. You can see that for this house here, that they were fairly accurate. The difference between what they estimated the house would sell for and what the house actually sold for was $500. And in other cases like this one, they were way off. There's almost an $80,000 difference between what they estimated the house would sell for and what the house actually sold for. You got your level of significance? Okay. So what is the claim here? Your mu0 value. This is what's going to determine the plus minus signs. Of the sign test. All right, so here comes the claim. Do the data suggest this estimate is inaccurate? Okay, so if the estimate is accurate, then the difference between the selling price and the Zestimate price would be 0. So this would mean that the estimate was accurate. Not equal to, it doesn't specify if it's inaccurate, is Zestimate going to completely underestimate the value of these homes or overestimate the value of the homes? There was no commitment to overestimation or underestimation, so that's why we just do the not equal to. So it's not equal to on average, then this would be inaccurate estimating going on. So do the data suggest that the Zestimate is inaccurate? We've got to call this one down here the claim. Okay, what I'd like you to do is just to take a couple minutes and calculate the following. Number of plus signs, number of minus signs, number of zeros, and then what is n, and then what is k, and in a two-tailed test like this, the value of the test statistic is going to be the smaller of the pluses or the minuses in a two-tailed test. Identify the critical value, and then based on what you find above, what is the decision? So this is going to be your paper and pencil work here. Very little calculator work. And if you have time, you want to calculate the p-value because your calculator is not going to do it. Well, there's no calculator function in the tests menu that'll do it for you. You do have binomial CDF that you can use. Okay, let's take a look. 0 is our boundary value, so anything that's positive will be larger than 0, and anything that's negative will be less than 0. So there's what your plus and minus signs will look like. we have 1, 2, 3 plus signs, and 1, 2, 3, 4, 5, 6, 7 negative signs, and no zeros. So the value of n is equal to 10. K is the smaller of plus signs or minus signs. So you got to pick out the smaller of 3 or 7. And the smaller is 3. For the critical value, alpha is 0.05, but it's a two-tailed test. So notice you have a 0.05 here and a 0.05 here. This is the 0.05 that you want because it's the two-tailed 0.05. In one tail, it's 0.025. So we're in this column, and we want to go down to n is equal to 10. So right there is your critical value, 1. K, critical value. K is 3, critical value is 1, K is greater than the critical value. So the decision is do not reject the null hypothesis. If K is greater than critical value, do not reject. So n is 10, alpha is 0.05, two tails. Go down and over, and you get critical value equals 1. It's from table XI. The p-value, binomial CDF, our n value is 10, always 1/2 for the p-value, and then our k value is 3. .172. P at 0.172 is greater than alpha at 0.05, and whenever p is greater than alpha, we do not reject. So this test, you can make the decision based on the p-value, you can make the decision based on the critical value. It's just a little bit different than what we've done in the past.